It is my pleasure to introduce the speaker, Yongqiang Tian. He's a PhD candidate from the University of Waterloo, and he's a final year student working on software testing and debugging, specifically focusing on testing and compilers and deep learning systems. And he's on the job market, so if you're hiring, consider hiring him. All right, let's go ahead.
Hi, everyone. I'm Yongqiang from University of Waterloo. It's my pleasure to present our work, Compilation Consistency Modular Debug Information. So let's start. Debug information plays a very key component in the software debugging. Specifically, it describes the relationship between source code and the binary programs. Using debug informations, we can easily know which line of source code is mapping to the binary instructions. So there are many studies working on debug informations, but most of them focus on one direction, which is how can we generate correct and complete debug informations during the compilations. So in our study, we want to pinpoint another problem, that is, the debug informations may interfere with the code compilations. Specifically, developer usually compile the source code without debug informations and use this binary program for productions. And developers will compile the binary program with debug informations and use this binary program for debugging. The problem is that here, the two binary programs may have different machine instructions. So let's look at a real example. Here, given this code snippet, if we use clone to compile this source code, you can see that with debug information and without debug informations, actually the binary instructions are different, which is highlighted in the pink colors. Specifically, enabling debug informations in compilation resulting into different machine instructions. Well, you may wondering why this happens. If we look at the function commit, actually it shows that compiler optimizers should get the next non-debugging instructions instead of get the next one directly. In other words, compiler optimizer does not properly handle the principles of debugging interest. So in our study, we use CCMD, or Compilation Consistency Modular Debug Informations, to refer this property. That is, compilers should always generate the same instructions, no matter whether debug information is enabled or not. You may be wondering why developers care about this CCMD. So I'll illustrate this using two examples. First, violating CCMDs may result into miscompilation bugs. For example, here, GCC will miscompile this load balance function in its kernels when debug information is enabled. Another problem is that violating CCMD will bring failures in debugging. As I just mentioned, developers usually deploy the binary program without debug informations for production purpose. And if it crashed, we will collect the countdown files. And we will recompile source code with debug informations and use this binary program with debug information and the countdown for debugging purpose. The problem is that when the CCMD is violated, JDB, and other debuggers will show many bad instructions over here. Instead, I'll tell you which source code is mapping to here. In other words, debuggers will fail to debug the faulty program when CCMD is violated. Actually, according to LLM developers are not actually debugging the exact same problem that has a bug we are looking for. Because of the importance of CCMD, both GCC and LLM developers care about CCMD. For example, GCC developers have a very special flag, compare debug, to check whether the debug information will affect the binary instructions. In other words, compiler developers strive to support CCMD. In our studies, we introduced the validation of CCMD to the research community. This helps us to avoid miscompilation bug, and this helps us to provide smooth debugging experience to developers. Specifically, the validation of CCMD is to find the program P and an optimization flag and two debugging information levels, such that the binary instructions output by the compilers are different. We also propose diffuser, the first technique to validate SysMD for C compilers. It aims to automatically find the program P that triggers SysMD bugs. Specifically, given a source code, we will do some mutation on it, and then we will compile it without debug informations and with debug informations. Then we compare whether they have the same or different instructions. If there are different binary instructions, we find the SysMD bugs. The problem is that how can we effectively and efficiently trigger SysMD bugs? As I just mentioned, the major action we did here is to do the mutations. So to design effective and efficient mutation operators, we need to understand why SysMD is violated. So let's go back to our previous examples here. As I just mentioned, one of the major root cause is that compiler optimizers does not properly handle the principles of debugging intrinsic. So based on this major root cause, we can design two intuitions. The first one is that we can mutate the program such that the program can trigger complex optimizations. Another part, we can generate a program such that this program have very complex debugging informations. So based on these two intuitions, we propose 3 mutation operators. I will introduce them one by one later, but in general, the first two is to generate program with complex debug informations. And the last one is to generate program triggering complex debugging, complex optimizations. The first operator we use here is called RCL, randomized code lowering. Basically, we will randomly lowering statements into smaller ones. For example, given code snippet shown here, we may randomly lowering the statement A equal to B plus C times D to 2 statements. And also, we may extract the not key from the if, or we can replace the if by a lot of go-to statement and labels. So by doing so, we can generate more variables in the debug informations, and also we can diverse the syntactic structure of the code snippet. Our second mutation operator is called OCP, obfuscation of the code positions, which is obfuscate the code positions to complicate debug informations. So here example, originally all the statements in this c.c file, they will have the file name c.c and line number from 1 to 3. So we can use some line directive here as shown here to change these informations. And after that, in the variant C, the first line will be in a.c and the line number is 1, and the other 2 lines is in another file called b.c. So using the line directive, we can easily to implement these obfuscations, and it is easy for debugging. Our last mutation operator is called FCO, file control of the optimizations. We randomly control the compilers. For example, given a function like foo here, we can insert some compiler attributes to tell the compiler always inline these functions. So by doing so, we can comprehensively access the optimization logic in compilers. So in summary, in diffusers, we use 3 mutation operators to generate program with complex debug informations and to generate program triggering complex optimizations. In total, our approach found 23 bugs in both LLVM and GCC, and 19 of them have been fixed, and 2 of them are confirmed. So we did some analysis on the root cause of these bugs. Specifically, we analyzed the 11 bugs that have a very clear fixed commit. We can analyze, we can understand, and we found that 4 bugs are actually in the middle end, and the 7 bugs are in the back end. This is in line with our intuitions. That is, the major root cause is due to the compiler optimizations, which does not properly handle the debugging informations. So we take one more step. We want to understand which of the mutations is the most effective one, and we found that all the mutations contribute to the bug detections. And among all of them, the RCL randomized code learning is the most effective one, and it finds 8 bugs without other mutation operators. We also studied like how did our mutation operators achieve their desired goal, that is generate complex debug informations and complex optimizations. Specifically, we analyzed the code coverage by 100 mutation program and 100 seed program. And we can see that with our mutation strategies, the code coverage is improved by around 5%. This shows that diffuser that can effectively access the code path in compilers. To understand whether our mutations complicate the debug informations, we also compare the number of debug informations and the diverse of the debug informations of 100 mutant program and 100 their seed programs. And we find that diffusers can effectively diverse the debug informations in terms of both amount and the diversity. So this is the end of my presentations. In our presentations, we introduce CCMD, compilation consistency modular definitions, a very critical properties for compilers. It can help us to avoid the miscombination bug, and it helps us to provide smooth debugging experience to developers. And we also propose diffuser, the first technique to test C compilers, and we found 23 bugs in GCC and LLVM. That is the end of my presentations. I'm happy to take any questions.